basically, I'm going to share my screen again. Okay, so if you go to, I think, if you go to the GitHub again, uh, if you go to week 1, go to QB hands-on. I'm going to paste the link into Zoom. I'm going to paste that link into Zoom again. Okay. You can go over here. You can click on the QP simple example. You can, and then press download. And this downloads the QP simple example over here. Next, you can go to the Jupyter Lab, which you all should have open from the QFT lecture. If not, please open it. Create a new folder. Okay, sorry. Seems to be lagging a little. Okay. Create a new folder. I'm just going to call mine QPE. I'm going to put the notebook inside there. I'm going to open it. Okay. So I have coded everything for you over here. There is nothing that you will need to fill up, but I'm going to go through a fairly simple example with you over here. So over here, okay, so we need to have the inverse QFT. We learned how to implement this previously. So the problem, okay, to reiterate the problem for QPE, given the unitary matrix U and the quantum state UCAT, where where these two are in this form, we want to find phi. Okay, and so for the simple example, we are going to consider the simple phase shift gate. According to the documentation, which y'all can see if y'all remember from the lecture the project gave yesterday, you can take a look at the gates and you can see what the phase shift gate implements. It basically implements the diagonal of 1 exp with phi over here. Okay. Phase shift over here. Copy directly, which means that if we implement this phase shift on the one cat, we get P, which I'm using P for phase shift over here. We get this. Okay. Okay. So right now, so we want to, so assuming that we have a certain phi, which I'm just going to call the angle over here, is a certain angle over here. I'm putting it in the initial phi in this form over here to make it a bit more similar to this, but you can see how you can convert between these two forms pretty easily just by adding the constant factor of 2 pi in front of it. Okay. So we can see how it works. And we know that we don't just need to be able to implement this unitary. We also need to be able to implement a controlled version of it, which is there is the control phase shift on top over here. The control phase shifts all exist all on the top over here. Okay, and so we know how to we know our U, we know our UCAT, and we know how to implement the control version of CU. note that we also need to be able to implement the control 2 to the power of j over here, which is actually really just running this running this multiple times. Running this multiple times. Note that this stuff isn't always necessarily the case. It just happens to be this for this a simple example. Okay, so the code for the QPE for the simple example over here is this. So we know that for the phase shift, we only need one qubit for the eigenstate. So remember, I said that this ucat can take as many qubits as it needs, but in this particular case, it only needs one qubit, and so we do one. Next, we want to know how precise to go, so we can define. I put this as a function. We can decide what our precision will be, and so this will be the number of qubits. So this is the number of qubits that we use for the first register. This is just some helping functions to help so the total number of qubits that we'll be using is the precision plus the unitary qubits, plus the qubits that we use for the eigenstate, which in this case is just however precise we want to go plus 1. Okay, then we declare the circuit. Next, step 1, we apply H to everything. Part of step 1, we also create the eigenstate. So I said previously, this is just kind of like step 0. This is something that we should have done previously. So we construct the eigenstate. So this is for the second register. This is for the first register. If I bring up the slides again, first register, I apply the H. Second register, I construct the ucat, in which in this case is just U1. It's just U1 cat. Next, we apply the controlled phase shifts. So in this particular example, we just apply this controlled phase shifts according to this angle. So right now we are pretending as if we don't know this angle over here. We pretending we know how to implement it, but we don't know angle. We're trying to find that out. We implement the control phase shift, and then lastly we do the inverse QFT. So we previously learned how to build the inverse QFT. Then we just take the inverse QFT is just the adjoint, and so we just do it. And remember, we are only doing it to the first register, so which is why the target is the counting qubits. Okay, and so this directly corresponds to this circuit over here. Okay, and with this, we can run the function. Okay, so right now we are getting angles. So right now this is just kind of like a simple example that a simple example that we are pretending to not know the answer, even though we are inputting the answer right at the start of it. So this is what we don't know and what we're trying to find. And in this case, we do like precision to the power of 3. Okay, so I should probably start running everything actually. Okay. So now we have this, and so right now we have initial phi, we have this, we declare a number of shorts if we want to use shorts. And then we just build the circuit over here. Okay, you can see in the first part, we built in the second register, Q3 is our second register. We have declared our eigenstate, and then we have created our superposition, a uniform superposition of states with all the H gates. Then we apply CU to the power 0, CU to the power of 2, CU2 to the power CU2 to the power of 1, CU2 to the power of 2, and this is the inverse QFT over here. Okay, and so when we run this, we see that if we read only the first we see that if we read only the first register, so in this case I measured a probability for this. If we read only the first register, we get that 0.01 is our state that we arrive at, which is one. What this means is that our what this means is that the state that we got back, so our phi that we got back, is 0.001 in binary. Does that make sense to everyone? What we get back is instead our angle is instead 0.001 in binary. And so when we calculate it, we get 0.125 for we get 0.125, and when we put it back into and we convert it back into the phi because of the angle predicted, where we just apply back the 2 pi constant, we can get back the angle that we put just now. And this is exactly the answer that we get over here. Now, what happens if as you can see, this is a pretty simple, pretty nice example because we can represent 1/8 pretty easily in terms of the binary form, the binary number system. So what happens if we do something, if we go with something that is harder to represent? Now, what happens if it's 1/3? 1/3 is not so easy to represent in this form, right? So what we do, I'll run it over again. And so what happens is instead, they get an answer, an approximation as close to 0.333333 as possible instead. And if we want to be more precise with our answer, we can instead go with 5. We can go with precision equals to 5. And we'll note that, okay, so when it gets to 5, this starts looking pretty unreadable. All of these things start looking pretty unreadable, which is probably why over here. And then I've constructed a helper circuit too. You can see that this is the phi that we have. You can see that with a higher precision, we can get closer to 0.33333 as we can go. And then the angle that we get will be much closer. As I say, approximation. And if we want, okay, this might take some time to run. Let's do 7 so that if we do 7, oh, they're not thinking. You can see where we can actually start getting pretty close. And it's in this way that we can define the precision of that we want and how close we want the approximation to be for QPE. Admittedly, this is for a pretty simple example, but this should give you a pretty big clue about how to play around with how QPE works. Okay, so I encourage you all to play with this novel game on free time. I have tried to make it as accessible as possible. All you really need to do, if you really want to just play with this simple example, all you really need to do is to play around with these values over here. I encourage you to play around with it to try and understand the implications of it as much as possible. So QPE leverages on basically the quantum Fourier transform in order to find that. And it's actually the QFT might be a subroutine of QPE, but QPE is actually a subroutine for other algorithms. Some of the some of the algorithms that you might have heard of are like Shor's algorithms, HHL algorithm, the quantum counting algorithm. All of these uses QPE in order to get that exponential advantage, which is really defined from which is really actually goes all the way back to QFT in order to get that advantage. I wanted to go through Shor's algorithm in more detail today. I don't think I'm going to have that so much time to go through Shor's algorithm, but I wanted to give you an intuition of why where QPE is used for Shor's algorithm. Okay, so Shor's algorithm is really an algorithm made for breaking RSA. And the RSA cryptography protocol basically is about Alice wanting to send a secret message to Bob through a channel that is not necessarily secure. In order to do that, Bob generates some public keys. Alice encrypts the keys using the keys that Bob generates. Encrypts a message using the keys that Bob generates. So Bob generates keys, he sends up a public key, and he holds a private key. Without the private key, he's not able to. Without the private key, no one else is able to decrypt the message that's encrypted with the public key. Alice encrypts a message using the public key that Bob sends out. He sends back and sends it back to Bob, and Bob can now decrypt that message using his private key. So how this normally works in reality is they are relying on the fact that prime factorization is difficult. And so that's the main way that the public key and the private key works. Is that the public key kind of encrypts it using a certain prime, and then because Bob has the other prime, he can decrypt it with his other one. And so this is the idea. So this is the idea behind encryption and decryption using the two primes that are created with the message. And so how to break RSA is really to find the two primes that Bob has. And since Bob is sending out basically the multiplication of P and Q, which are the two primes, which is to Alice. If Eve can break down the two primes into P and Q, and she knows what the two primes are, she now has a copy of the private key that Bob has. So Shor's algorithm is really an algorithm for prime factorization over here. Okay, so here's the pseudocode for Shor's algorithm. It's a prime factorization algorithm, and it is actually mainly classical. In fact, you can see in this entire pseudocode over here, there is only one part where it's going to be quantum. And that's this order finding algorithm. Everything else, when you check for trivial cases, is all classical. Choosing a random integer, classical. Checking if it's R is even, classical. Checking for this, checking for this, checking for this. Everything is classical except for this order finding algorithm to find the order of R such that a to the power of R equals 1 of n. Everything else, and this will give you your prime factorization. And so actually Shor's algorithm is a code that is for prime factorization, and even a subset of that, one of the steps is the order finding algorithm, where the quantum part works. So the order finding algorithm is really just two steps. One is that we have this unitary that we can apply to this, and the second part is the continued fractions algorithm. I will not be going through the continued fractions algorithm because this is also a completely classical part. So as you can see, with the entire Shor's algorithm construct so much pseudocode, so many parts, but really there's really only one step that is quantum, that requires a quantum computer. Everything else just requires the classical computer. So the purpose of QPE is given a unitary matrix U, quantum state UCAT. We want to find this theta. How it applies to Shor's is that now we are given this unitary matrix U over here. They find a way to construct an eigenstate of U over here on the second step, such that U to the power of U applied to this eigenstate over here. So we have a unitary matrix that is defined by this certain function. They find a smart way of constructing an eigenstate, and we find out that the eigenstate is basically 2 pi I s over r over here. And so the purpose of QPE over here, when applied to Shor's algorithm, specifically to this eigenstate, is that we can find the value of s over r. This is the entire kind of like quantum finding algorithm that you can see in Nielsen and Trong. It's the QC textbook. I highly recommend. I do recommend looking at that textbook if you have the time, if you are serious into getting more into quantum computing. But you can see that the QPE really only happens all over here. We create a superposition. We apply the unitary matrix, the control unitary matrix to a way that we can to the eigenstate, and then we can get S over R. No, we can get S over R too, because again, this is an approximation. Now with S over R, we can apply the continued fractions algorithm. This is completely classical. You all can read it up yourself to get R. And this is how we can get the order over here, because what we wanted to do is we wanted to find the order R. Okay. And so obviously the non-trivial questions you have to ask for Shor's algorithm is how we can apply U, how we can apply the control U, how we can apply the control U to the power of 2 to the power of J. And actually that's where a lot of the research for QPE and Shor's algorithm is done. We remember that QPE is a pretty popular subroutine to apply to everything, to apply to a lot of different algorithms. And so there is going to be a lot of value if you are able to find an efficient way of applying QPE for a general unitary matrix, of being able to find an efficient way of constructing U to the power, U to the power of 2 to the power of J for matrix. However, you can also take a look at the individual applications for it. For example, Shor's algorithm, where you can take a look at how to apply this U to the power of 2 to the power of J for specific applications. And so constructing QPE in a smart way that works only for one application. And so these are two very active areas of research that is currently being done for QPE. Okay. If we were to look at the advantage for Shor's algorithm, I implemented it before. This is actually a pretty bad implementation of Shor's algorithm. This implementation. This implementation is actually pretty smart, but it's quite hard to understand mathematically. Instead, I implemented a pretty stupid version of Shor's algorithm, but you can see that as the number of n grows exponentially, the number of qubits grow linearly, and the circuit depth grows polynomially. Uh, for comparison, the best classical algorithm for prime factorization is the general number field sieve. At this point, obviously, this is the best classical algorithm that we know at this point. At this point is an exponential term. And so theoretically, the best number of operations required for this is this. And so this is where this log advantage, exponential advantage comes from. You can see there are there's a lot of active areas being done for Shor's algorithms in order to study it. It is also common, it is also commonly thought there's a very popular paper that kind of did the resource estimation for Shor's algorithm. It is commonly thought that 20 million qubits is a threshold for advantage for Shor's algorithm because so that it can implement RSA 2048. This advantage comes from this 20 million qubits comes not from the fact that this 20 million qubits are all going to be clean qubits. This 20 million qubits also takes into account the error rates, the noise, and stuff like and logical qubits. And so the number of qubits used with every passing paper on Shor's algorithm grows lesser. The number of noisy qubits that is required in order to have one logical qubit grows lesser as well. And so even though Shor's algorithm would not provide any advantage in the short term, because one, we don't have the hardware, all our devices right now are noisy, which is going to be a huge problem because you see that the circuit depth over here grows polynomially is like 50,000, even just for n is 187 over here. If you're performing 50, having a circuit depth of 50,000 is basically basically a one-way road, making sure you have nothing but noise at the end of the day. The 20 million qubits can be used to perform some quantum error correction. The noise threshold is starting to get better nowadays. People are starting to get smarter about quantum error correction and mitigation, and they are also improving the algorithm for Shor's. And so actually, 20 million qubits might not be this threshold anymore. This resource estimation was done in 2020, I think. And so as the years goes by, it's also commonly thought that this threshold will go down. Okay, and with that, I hope that I impressed upon you all how to run QPE. I hope you all got the intuition behind the 3 steps behind it. And I also hope that you with me just briefly going through Shor's algorithm, you can see the QPE in action for it. What I hope that you do in the meantime is I hope that you play around with the notebook I gave you. It's done for just a really simple example, but I hope that you can play around a bit, play around with precision, play around with angles, play around with the other and play around with other unitaries that you can think of, and get a better understanding of how QPE works.